Okay, good afternoon. Can we begin? Hello.
Yes, sir.
Good afternoon, Professor. We can surely begin.
Okay. So, by the way, I have already written to WhatsApp that coming Thursday we will have one quiz. Okay. So, how to organize this quiz, etc. We'll talk about it on Monday. Is it okay, na?
Sure,
Hello.
sure.
So
Yes,
if
sir.
you have any such, I am not very experienced in conducting quiz through online process. So if you have any specific idea or experience, please share with me. Okay. So accordingly we can move on. Okay. Now let us begin where we ended. So essentially in the last class, just a kind of recapitulation little bit in the beginning itself so that you can get the right space to move forward. So we started talking about the ESR profile based on the fact of the metal complexes. So what I said so far, that in case of metal complexes, basic principles remain the same. Only the complexity develops because of variety of factors. So one of the important factors in that case, as we started talking about, the isotopic pattern, and particularly the isotopic abundances, their ratios, and their MI factor. And keeping all these things in mind, then your MI-MS interactions would become a little bit more complicated compared to what you know about the radicals or organic molecules. So we need to understand that factors together. And on top of that, we would have the situation where the molecular distortion would come into the picture of electronic configuration. Now, when we talk about the molecular distortion, that based on the fact of the geometry of the molecules and how it is being distorted along the Cartesian axis based on the donor symmetry, donor asymmetry, chelation factor. There are so many factors, as we already aware of it from our very basic inorganic chemistry point of view, all would come into the picture together. And that will make the things much more complicated. Now, if we see the, just a second, yeah. So what we have talked about, that if you have the metal center, which is having carrying only unpaired electron, it does not have any magnetic nucleus. In that situation, it follows the super hyperfine splitting pattern under the broader banner of equivalent centers or inequivalent centers. So all would come into the picture. Already we have talked about it. And accordingly, the lines would start splitting, splitted in a very selective and designed fashion. I'm not very sure that that always you would be able to see this kind of crystal clear spectral profile. Okay, this is the ideal situation one could think about. And when you go for recording the ESR profile of your compound, you would be noticing that there are occasions you would be getting what you could anticipate out of your theoretical background. But there are many occasions you would come across where you would be encountering not so well-deserved situations. We know why. Already you have talked about it. Now there is a question in the WhatsApp, I think after the last class, that doping pattern. Okay, so I'm not answering that question right now. What we will do, there is one more example I am having at the end of this, the later part of this particular talk, and there we'll discuss at length, and I hope you would be happy to understand that process. Now, we also talked about the simple situation where instead of super hyperfine splitting, we have talked about the hyperfine splitting pattern. That does mean that the same metal ion carrying the unpaired electron and carrying the nuclear spin, and then it is the vanadium 4. So one line would be splitted into 8 lines as per the standard rules, and then you will have the hyperfine constants. And there I made one point that if there is no further interactions under normal circumstances, one could expect to have a symmetric A. And symmetric A means one A can represent the rest of the A's. So you need not to worry about A1, A2, A3, etc. Only A you need to mention. But if you see that A's are not identical or similar, then you need to mention all the A's. Then if you go for a polynuclear setup, like V2 setup, what I said, and there you will have the further complications in terms of the number of lines, and based on the geometry you will have, if you have the tetragonal symmetry over there, then you can expect to have further splitting based on the geometry. As I mentioned, the geometry, distortion, John-Taylor effect, all sort of things, and then you will have the separated segment within the spectrum, that is called parallel segment and perpendicular segment. We'll talk about it a little bit later. So all these things, but this kind of situation you should not, or you won't expect out of your organic molecules. Okay, here that the ligand is essentially very close to the free electron situation, and if it is a free electron situation, you have the interactions, that means electronic and nuclear interactions, but you won't expect to have the additional distortion in the spectral profile due to the molecular distortion, the factor which is very common for metal complexes. Now, this is the thing we started to speak about, the isotopic abundances. So I said just one particular example we have picked up, the simple copper tetracoordinated system. And if you look at the copper system, there are two isotopes and both are magnetically active. Okay, but the good point is that both having the same I value. So in both the cases, you will have 4 lines, no problem. Only the intensity of line would be proportional to the natural abundances of those isotopes. And here it is roughly 1/2. Okay, and you have been seeing that 1/2 intensity ratio between the isomers. But again, as I said, that what you can expect out of your theoretical consideration, that may not always be reflected well as far as the experimental feature is concerned. So instead of this kind of distinct spectral separation, you would be seeing a kind of overlapping. You could see it. So a kind of overlapping you would be seeing over here, and this overlapping, you see that here it is a better result, but here